Let's look at this question. This question involves a combustion chamber with hot gases in it. Temperature of the hot gases is T, infinity velocity is V. We use this thermocouple to measure the temperature of the hot gases. Ideally, of course, we like the temperature of the thermocouple to reach T infinity, so it gives an accurate reading. How long does it take for the thermocouple to reach T infinity from its initial temperature, Ti? Yes, it will take infinite amount of time to reach T infinity from Ti. But given time, it can approach T infinity asymptotically. In this question, we want to estimate the time required for the temperature to reach a certain temperature. So of course, this is a transient problem. So it involves chapter 4. Remember in chapter 4, we have this equation that gives us relation between temperature and time. And remember that equation is only applied to lump system analysis. So we need to make sure Bell number is actually smaller than 0.1. And Bell number is HL over K, so we do need the H to find the Bell number. So don't forget, we will need to verify the Bell number. So we want to find the time required for the temperature difference T infinity minus T to reach 2% of the initial temperature difference. Initially, the thermocouple is at temperature Ti. So the initial temperature difference is T infinity minus Ti. So again, what is T infinity minus Ti? Given infinite amount of time, eventually the temperature of the thermocouple will reach T infinity. So T infinity minus Ti is the maximum temperature difference this thermocouple could ever experience. Then how much time does it require for this temperature to reach 2% of the maximum temperature difference? Which equation should we use? Yes, we should use that one equation from chapter 4 that gives us the relation between temperature and time. So if we write time, it would look like this. What is the value of this? From this equation, we know Ti minus T infinity divided by T minus T infinity is 50. It's 1 over 2%. Then let's write the time. Rho V is the volume of the spherical ball. We treat the thermocouple junction as a spherical ball. The volume is 4 over 3 pi r cubed. And the surface area is 4 pi r squared. This is 50. Let's cancel out the r squared, cancel out the 4. And this would become diameter density multiplied by C divided by 6, the average convection coefficient, and we have natural log of 50. Okay, now we need to find the H. If H was given, this would be a typical problem from chapter 4. But now H is unknown. We need to use knowledge from chapter 7 to find the H. So how do we find this H? We have one correlation for external flow over a sphere. Let's write it down. Now let's plug in numbers. The problem has given us the properties of the combustion gases. We can just neglect this viscosity ratio between T infinity and Ts. Reynolds number is VL over mu. So what's the characteristic length in this case? Note, when it comes to external flow over a cylinder or sphere, the characteristic length is simply just the diameter of the cylinder or the sphere. So it's VD over mu. Prandtl number is provided as 0.69. Then we can calculate over h. What's the relation between Nusselt number and h? H is k over d multiplied by Nusselt number. I want to emphasize again, when it comes to Nusselt number, the characteristic length is also the d. So another question, what about this k? This should be the thermal conductivity of the solid material or the thermal conductivity of the gases. Yes, in Nusselt number, the k is the thermal conductivity of the fluid. In Bell number, the k is the thermal conductivity of the solid. So now we have the convection coefficient. We can check Bell number. Bell number is h multiplied by characteristic length divided by k. What's the characteristic length of a sphere when it comes to Bell number? That is radius divided by 3. Whose thermal conductivity is this? Again, this is the thermal conductivity of the solid. This is 100. And find out this is much smaller than 0.1. So we concluded the log system analysis can be applied to this case. So then we can use this equation to calculate the time required for the temperature to reach 2% of the maximum temperature difference. Now let's plug in numbers. So T is So we concluded that it takes about 7 seconds for the temperature difference T infinity minus T to reach 2% of the possible maximum temperature difference.